So today we are going to learn about electromagnetic waves. The electromagnetic waves, the concept of electromagnetic waves came into existence when Maxwell tried to unify electric and magnetic phenomenon. Before Maxwell, electricity was a different idea, magnetism was a different topic, they were alien to each other, and Maxwell unified these two theories. So this lecture will have two parts. First part we will concentrate on how the electricity and magnetism are the same, are the two sides of the same coin, that is how these two subjects can be unified. And second part, the properties of electromagnetic waves. So Maxwell deduced electromagnetic waves by purely theoretical means. No experiment was done at that time. So theoretically also we can derive. So Maxwell introduced the idea of displacement current to explain origin of electromagnetic waves. Now displacement current. So first let us see displacement current. So let us see how Ampere's law can be applied to varying electric currents. We will take the example of a charging and discharging of capacitor. So suppose this is my capacitor and this is charged, or we may discharge it through a resistor. When we press the key, the current begins to grow, current increases with time and the capacitor gets charged. So during charging, how the magnetic field will be built up in this region and this region we will study. We will apply Ampere's law on the current, that is time varying current. So let us see that suppose this is my capacitor. This is my capacitor plates. So this is the positive terminal of the capacitor plates and this is the negative terminal of the capacitor plates. The capacitor suppose is in the process of charging. So the current flows in the capacitor this way. The charge build-up take place on the capacitor plate, and here this is the positive plate. So the charge flows from this towards this. So we will concentrate in this region and in this region. Now suppose, let us see, take a point very close to this wire. Now when the current flows, there is a magnetic field build up in these locations, and the magnetic field B can be calculated by Ampere's law. We will use Ampere's law to calculate the magnetic field at this point. So we expect the magnetic field at this point to be something like this. That is, in order to calculate magnetic field B at this location, I am going to use Ampere's law. Now what is Ampere's law? Ampere's law tells that the line integral of the magnetic field in a closed loop is equal to mu naught times I enclosed. So we will use this Ampere's law to find the magnetic field at this location. So we will have another diagram where we will concentrate on the loop. Suppose this is my capacitor plates and this is my wire, and I want to know what is the magnetic field here. The current flowing is here, the capacitor is being charged, this is positive plate and this is negative plate. So now if I consider a Amperian loop, this curve, let us denote it by C. Then if I apply B dot dl, then it is equal to mu naught enclosed. Now you see here current enclosed means the current must cross the boundary of all the surface whose outer boundary that curve. That means here you see the current is I, that is conduction current, the current flows in this wire. So if I consider a surface here, this surface is called S1, then the current IC crosses the boundary of this surface, and I say that my curve encloses this current, and so their B dot dl is finite, and so we can calculate the field existing in this region. Now if we place a compass, magnetic compass here, it will get deflected, and this proves that there is a magnetic field due to conduction current here. Now suppose if I take this surface like this, if I take this surface like this, then we see that this is S2 surface, no conduction current crosses the boundary of this surface. That means if there is no conduction current here, that means B dot dl is 0. So if I see right way, this way, from S1 surface I got there is a current enclosed and B dot dl is finite. But when we see this way, then we don't find that mu enclosed, there is no current enclosed. That means there is some flaw with this equation, Ampere's law. Now Maxwell further thought that if, according to Faraday, electricity can be produced by a changing magnetic flux, then magnetic field can also be created by electric flux. So electricity can produce magnetism and magnetism can produce electricity. So if this is possible, then there will be a complete symmetricity in the system, and so electricity and magnetism will be the same sides, different sides of the same coin. That means unification of electricity and magnetism can only be possible if we consider that electricity is produced by magnetism and magnetism is also produced by electricity. So that means there is something. Now one more thing, in the capacitor, in between the capacitor, we have magnetic field without any current. Now this can only be explained if we assume that the electric field which is set up in this capacitor is also capable of producing magnetic field similar to the magnetic field produced by electric current, that is the conduction current. So this was the idea conceived not on experimental basis but on the theoretical basis by Clerk J.C. Maxwell. Now let us predict what modification is required in this Ampere's law, Ampere circuital law, to accommodate the magnetic field produced by time varying electric currents. Because you see, this law we have derived from Biot-Savart law that are purely due to steady currents, but now we are trying to apply this law when the current is changing. So we require certain modification, and we should let us predict all these modifications theoretically. Now you see, this is our capacitor, and in this Q and minus Q is some instantaneous charge on the plates of capacitor. The electric field E, electric field here E will be equal to sigma by epsilon naught, which can be written as Q by A epsilon naught. Now this rate of current I is equal to dq upon dt. This is the conduction current. Now in this region I, in between the plates of the capacitor, we have the electric field changing whenever current I changes. So suppose I write this Q, this E as Q by A epsilon naught, then in that region the field will be changing at the rate of 1 by A epsilon naught dq by dt. Now you see this dq by dt, suppose I write this as I d, then it is, that is again A epsilon naught dE by dt. Now this id will become let us include A inside it, so it becomes A into E dt, and since they are perpendicular, the electric field and area vector, so this we can write as flux of electric field. That means, so this id here is a fictitious current inside this capacitor. This current we will call as displacement current. Displacement current. What is this displacement current? This is a fictitious current flowing in between the capacitor, where actually the field, electric field, is changing with time. Now the changing electric field is capable of producing magnetic field as the magnetic field as the field produced by a conduction current. So we call this as displacement current epsilon naught dE by dt. Now you see here, now we have a modified, I can modify my Ampere's law, which was previously I enclosed. Now the region in which there is a change in electric field, where there is no conduction current, will be, I will write this as I displacement or simply ID. Let us denote the time varying current as small IC. Capital I will reserve for constant current, mu naught ID, where this ID is the displacement current. And so we will have B dot dl is equal to mu naught IC plus mu naught ID is epsilon naught d phi E by dt. This is the modified version of, that is the Maxwell's version of modification of Ampere's circuital law. Now here, now with this addition here, we can accommodate in Ampere's law the possibility of time varying fields. Let us see how. Now this is our charging capacitor, charge capacitor. Now we wanted to know what is the magnetic field, or we in this, on this curve C, if we are interested to apply Ampere's law. So if I select our surface S1 this way, then you see the current IC crosses the boundary of this surface, and we will say we can apply directly B dot dl is equal to mu naught IC plus mu naught epsilon naught d phi by dt. Now if we select this surface S1, there is no changing electric field within this region, so this quantity is 0. I will write only this one. This term will be retained only for this surface. But if we select our surface this way, S2, then there is no conduction current, and we will write B dot dl is equal to mu naught IC plus mu naught epsilon naught d phi E by dt. For this S2 surface, this quantity is 0, and so we will simply write B dot dl is equal to mu naught epsilon naught d phi E by dt. So the very idea that Ampere's law can be used also for time varying fields, we can use this idea provided we accommodate this term. that is the role of displacement current. So, what we can say is, you see the field is changing here. This changing field is capable of producing magnetic field, and so we can call that there is a fictitious current flowing from this side to this side in this charging capacitor or even discharging capacitor, which produces the same magnetic field which a conduction current can produce. Now, it may be possible that in certain regions there will be some conduction current and some displacement current. So, we will include both these terms there. Now, let us see that if a capacitor is being charged, then what is the field within this region, and the field comes from what components? So, this is your positive terminal and this is the negative terminal, and this is in between the plates. So, the field is in between the plates is like this, and here there is a conduction current IC and conduction current IC. Now, there is also some radial current going in the capacitor plates. The capacitor is in the process of charging. So, in a certain region here, the field is due to this current, conduction current, this is conduction current, this is the conduction current, this is the conduction current, this is the conduction current, and there is a displacement current. So, if I want to know B here, then I have to take the contribution of all the current. Here there will be conduction currents and here will be the displacement current. So, in any region we have to take the contribution of all the components. So, now let us see how to calculate the magnetic field as a function of R in between the parallel plate capacitors. So, you see this is IC, some current is flowing, and suppose at some instant the charge is Q and minus Q, Q and minus Q. So, what happens? I am interested in calculating the magnetic field at this place. So, I have taken a Amperian loop. So, electrical fields cross this boundary. This is R, and we will calculate what is B, maybe in this direction or that direction. Suppose I say it is B like this. So, we are interested in B as a function of R. So, let us magnetic field, or the heading is magnetic field inside a charging capacitor. Now, this capacitor, let us suppose this is the capacitor which is not charging or a discharging capacitor. It is being discharged through a resistor R, and at some initially it was having charge Q, and at some instant it has a charge Q and minus Q. So, I know that the current I will be given by, that is initial charge Q by R e raised to minus T by tau, where tau is equal to CR, that is the time constant. This is how the current will vary through this. Now, let us at some instant the charge here is Q and minus Q. So, the electric field becomes Q by A epsilon naught, and if I apply here, applying Ampere's law, let us apply Ampere's law, then we will write this as B dot dl is equal to mu naught IC plus mu naught epsilon naught d phi E by dt. Now this quantity is going to be 0. B I am interested in. Due to symmetricity, B is constant. It comes out of the integral. dl means it is 2 pi r, and this is mu naught epsilon naught d phi e. The electric field is d by dt of, this is pi r square, this is constant. So electric field is q by a, let it be a into electric field, that is q by a epsilon naught. This cancels out. So this becomes 2 pi r mu naught epsilon naught times dq by dt, that is epsilon naught also get cancels from here. So dq by dt is the current. So we have B is equal to mu naught I by 2 pi r. This is the magnetic field within this region. We want to know what is I. I can be substituted from here. So we have mu naught by 2 pi r. I is q by r e to the power minus t by tau. This is what. So here you see, we are able to calculate what is the field within this charging or discharging capacitor with the help of displacement current. That means theoretically we are able to establish that magnetic field can be produced by electric field. Changing electric field produces the same magnetic field which a conduction current can produce. So this is what the displacement current is and how the displacement current can produce magnetic field in a region. Now you see here, so now Maxwell introduced, rewrote the equations of electrodynamics as Maxwell's equation. Maxwell's equation. Now Maxwell's equation is, first, E dot ds is equal to q inside by epsilon naught. This is Gauss's theorem, Coulomb's law, Gauss's theorem, same thing of electrostatics. Now from magnetostatics, B dot ds, this is the closed surface, will be equal to 0, that is Gauss's law of magnetism. Now this law predicts that magnetic monopoles does not exist. Next is Faraday's law, which tells E dot dl, that is the EMF induced, it's not closed, EMF induced will be equal to minus d phi b by dt, that is Faraday's law. Faraday's law. Next one, the Ampere's law itself, B dot dl is equal to mu naught I conduction, that is enclosed conduction current, plus mu naught time epsilon naught d phi e by dt. Now you see this term, this is modified Ampere's law. This is modified Ampere's law. Now with this modification, Maxwell was able to unify electricity and magnetism. So the outcome of unification of electricity and magnetism was that it could predict a self-sustaining electromagnetic wave. That is, a changing electric field in space can produce a magnetic field, a similar magnetic field and in turn the magnetic field can produce. So, there is no requirement of medium, a self-sustaining wave can be produced. Now, let us see how that wave can be produced. Now, this is Maxwell's equation in when there is a current IC and charge. Now, Maxwell's equation in a region with no charge and no conduction current. Now, suppose there is no charge, then this will become 0. B dot ds is 0, this is this, and when there is no conduction current, this term is not there. That means only this term is there. There are 4 set of equations in the region where there is no net charge and net current. For example, our charging capacitor or discharging capacitor, you see here there is a time varying field. It is time varying field, but here there is no charge. On the capacitor plates there is a time varying charge, but in between this region there is neither any current nor any charge. So, how field and how E? So, in this region there is a combination of E and B. So, how E and B will behave in this region can be calculated by all these 4 equations. This was done by Maxwell. So, we are not going to solve these equations. So, we are just interested in the solution of these equations. So, now we have seen that Maxwell's equation in charge free and current free region. Now, if I solve these equations, we will get a coupled partial differential equation of first order. Let us see. This is your z axis, or call it x axis, y axis and z axis. So, the equations, the previous equations predicts that there is a self-sustained electromagnetic field. Self-sustained means, you see, this is E field. E field, you see, E varies sinusoidally. This is E field. So, E varies, and you see a similar B field is also there. So, E field and B field. Now, this E can be written as E is along Y. So, EY is equal to E naught sin omega t minus kx, and EZ and BZ is equal to B naught sin omega t minus kx. So, this is the direction in which the wave propagates. The wave velocity is given by, we will denote it by C. C is the letter reserved for velocity of electromagnetic waves. C as omega by k. Omega by k, where omega and k is related as 1 by root over mu naught times epsilon naught. So, C is, thus we see that C is 1 by mu naught epsilon naught. So, Maxwell could derive these equations from the previously discussed 4 Maxwell's equation, and the result was that there is a self-sustaining E wave and B wave. Electric field and magnetic field are orthogonal to each other, and electric field, B field and the velocity vector forms a orthogonal system, right-handed orthogonal system. The essential part of this wave is that they don't require any medium. The velocity depends on, in free space, the velocity of this wave is 1 by root over mu naught time epsilon naught, where mu naught is the permeability of free space and epsilon naught is the permittivity of free space, and they are mutually perpendiculars. You see, the waves here I have shown is a sinusoidal wave. E is also sine and B is also sine. It may not be sine, it may be some other functions or exponential function or other function depending on the motion of charge which has created this type of electromagnetic field. Now, when this field propagates in some medium, in any medium apart from air or vacuum, then the velocity will be written as 1 by mu and E, that is 1 by root over mu naught mu r epsilon naught epsilon r, that is 1 by root over mu naught epsilon naught times mu r epsilon r. This is itself C. So, V is equal to C by root over relative permeability and relative permittivity. So, we can use the velocity of electromagnetic waves in a medium. You see, the medium should be non-conducting and non-ferromagnetic medium. So, the velocity will be V. Now, we also define in optics the refractive index of a medium as mu as velocity of light in air or vacuum by velocity of light in the medium. And so, you see, refractive index mu also comes out to be C by V, that is root over mu r epsilon r. So, in this way, Maxwell was able to unite electricity with magnetism. The celestial marriage between electricity and magnetism was possible by Maxwell. At the same time, he was able to link optics with electromagnetism, and the origin of light, that light is also electromagnetic wave, was established. Now, let us see how this electromagnetic wave carries energy and momentum. So, now let us see the energy carried out by electromagnetic waves. So, whenever a charge build-up takes place, whenever a charge is under acceleration, then there is a electromagnetic wave emitted by it. So, let us see how electromagnetic waves carry charge or energy. Energy carried or energy density and intensity of an electromagnetic wave. From electrostatics, we know that the electrostatic field energy, the energy associated with electric fields, is given as epsilon naught by 2 E square, and the energy is also stored in magnetic fields with energy density UB as B square by 2 mu naught. So, the energy density of the electromagnetic waves we will denote by U, will be given by UE plus UB. The energy is stored in electric field and B. Now we use this as UE as epsilon naught by 2 E square, and this is B square by 2 mu naught. I think one thing I missed about, let us write about electromagnetic waves, that E is equal to E naught sine, E was equal to EY, that was XY, EY was equal to E naught sine omega t minus kx, and I wrote BZ is equal to B naught sine omega t minus kx. Now this E naught and B naught are related as B naught is equal to E naught by C. This is how the magnetic field amplitude B naught and E naught is related. We can further change it as B can be written as, so let us do one thing more. Now this electric field is a sinusoidally varying field, and so when I am calculating the energy density, we are interested in RMS value of this electric field. So we will be using it. ERMS will be equal to ERMS, simply I will write, or ERMS will be equal to root 2 times E naught, or let us write it by E naught only, E naught by root 2 plus 1 by 2 mu naught B naught by root 2, that is the RMS value. U is equal to epsilon naught by 2 square of E naught by root 2 plus 1 by 2 mu naught, that is RMS. We will write this RMS. RMS is E naught by root 2 and B naught by root 2. So we will write this as E naught by 2 into E naught square by 2 plus 1 by 2 mu naught B naught square by 2, that is epsilon naught E naught square by 4 plus 1 by mu naught 4 by mu naught B naught square. B naught square now can be written as E naught square by C square. C square can be further written as mu naught epsilon naught, mu naught epsilon naught, mu naught cancels. So we have epsilon naught E naught square by 4 plus epsilon naught E naught square by 4, that is epsilon naught by 2 E naught square. So we got U as epsilon naught by 2 E naught square. So this is the energy density U which we got, the total energy carried out by this wave. So now you see here that intensity of the wave is the amount of energy transported per unit area per unit time, that can be written as energy density into wave velocity. Energy density into wave velocity. I is equal to, energy density is here epsilon naught by 2 E naught square and wave velocity is C. So this is epsilon naught C E naught square by 2. So this is how the energy is carried out by a electromagnetic wave. Now if a wave is capable of transferring energy, energy is called the surrogate of momentums. That means if a system has energy, associated with it, then there must be some momentum associated with it. And so, the momentum associated with electromagnetic waves, the linear momentum and angular momentum is also associated, that we will see later on. So, thus these electromagnetic fields possess energy and momenta also. So, next we will see the momentum possessed by this, that is, we will see what is radiation pressure.